Hello there, Algebra 2, and here we are. We're about to do the Chapter 5 Review number 2 worksheet, and I'm going to allow skipping on this so you can skip ahead to whatever part you need. But I'm going to do the whole thing, beginning to end. Here we go, rock and roll. Number 1A. Well, this thing here is in log form. I find log form scary, so I change it to exponential form and make this 2 to the 4th equals x plus 5. And then it's just a calculator problem. I happen to know that 2 to the 4th is 16 equals x plus 5. I do a little math, subtract a little 5, and x is 11. Yeah, baby, we're good. Taking a look at number B. Number B, I spy 2 log statements that are being added. And so if we are adding log statements, that means we multiply the guts. And so I would write this as log base 2 of, let's multiply, x minus 5 times 8. So 8x minus 40 is what the log statement is of. And it equals 7. And now that it's a single log statement, I can rewrite it in exponential form. That means 2 to the 7th equals 8x minus 40. And 2 to the 7th is, well, let's see, 2 to the 4th is 16, 32, 64. I want to say 128, but you guys have calculators. Equals 8x minus 40. And if I add 40 to each side, I add 40, I get 168 equals 8x. And oh my gosh, I can't do this part in my head without cheating and looking at a calculator, because 8 goes into 160 20 times, and there's another 8, so x must equal 21. I'm going to go check that. Nope, we were rocking and rolling. Number C. Number C, again, I see 2 log statements, so I'm going to combine them by multiplying log base 6 of 8x, 8 times x, must equal 3. Again, I'm going to put this in exponential form. 6 to the 3rd equals 8x. 6 to the 3rd is a big number. It's 36 times 6. Oh, I don't know. I'll get a calculator. It is 216. So 216 equals 8x. I think 8 is going to go into this evenly also. I'm going to see if I can do this in my head. Let's see. 80, 160, that's 20 times. And then another 40, 200 would be 25 times, 26, 27. I think x is going to be 27. I'm now going to check on a calculator. 216 divided by 8. Booyah! I love the power of math. Let's take another. Number dog. Number dog says, again, I see some log statements being added, so I'm going to multiply whatever it's the log of. So I get log base 3 of 81x equals 1. And if I rewrite this in exponential form, that means 3 to the 1 equals 81x. And if I'm solving for x, I'm going to divide both sides by 81. And I get x equals, well, let's see, 3 goes into both of these because this is 3 to the 4th. 81 is 3 to the 4th. And so if I cancel, I should have a 1 on top and a 3 to the 3rd on the bottom. So I get x equals 1 over 27. I'll check the answer key. That's what I put. Number E. Again, we see some log statements being added. I remember I did this in class, but just in case we're doing this again next year, we have log base 3 of, so again, I'm going to combine them by multiplying what it's the log of. So x minus 2 times x plus 6 equals 2. Again, I'm going to write it in log or exponential form. This means my base 3 to the 2 equals this stuff, which I'm now going to multiply out, x squared plus minus 2x plus 6x, so plus 4x minus 12. I could rewrite 3 squared, and I can do that in my head. I'm so powerful. 9 equals x squared plus 4x minus 12. And so if we subtract 9 from each side, I get x squared plus 4x minus 21 equals 0. And let's see, then we can factor it. X minus 3 and x plus 7, I believe, will get me the positive 4 in the middle. So that means x must equal positive 3 or negative 7. Now, even though those are my answers, whenever you have logs, problems with logs in them, you should check to make sure your answers work, and I haven't been doing that. If I plug in 3 here, I plug in 3 for x. Yeah, just erase this and plug in 3 for x and check to make sure this works. What we get is log base 3 of 3 minus 2, so of 1, plus log base 3 of 9 equals 2. So let's check. 3 to what power is 1? 3 to what power will get me 1? Well, that is 0. 3 to the 0 power is 1, so this is 0. Plus 3 to what power is 9? 2. 3 to the second, and so sure enough, this checks out. Now, if what I do is now plug in negative 7, 3 checks out. We're happy with 3. I'll give it a red check. There. Red check. Yay. Oh, shoot. We'll even give it a smiley face. If I do the same thing and I plug in negative 7 for x, so negative 7 goes there and negative 7 goes there, what we have is log base 3 of negative 9 plus log base 3 of negative 1 equals 2. Well, and this thing here says 3 to what power is going to get me negative 9? And hopefully you know this has no solution. 3 to any power, if you graph the function y equals 3 to the x, 3 to any power looks like that, and it has an asymptote on the x-axis. So this never even passes into the negative, so it can never equal negative 9. Just like it can never equal negative 1. So this has no solution. So that's why we eliminate negative 7 as a solution. Whew, long explanation. Let's move on to part F. So part F is this. It says we have 2 log statements that are being subtracted. So we can combine these guys by dividing. So it's log base 3 of x minus 1 over 4 equals 3. And then again, I'll write this in exponential form. That would mean 3 to the third is x minus 1 over 4. That's 27 equals x minus 1 over 4. I am going to use the powers of mathematics to get rid of that fraction and multiply both sides of my equation by 4. Wackadoodle. X minus 1 equals 27 times 4 is, let's see, 20, that's 80 and 28, so 108. If I add 1, x must equal 109. I don't remember seeing that as an answer, but there it is. Woohoo! Let's move on to number 2. Let's see. Well, first off, if we're going to solve for x here, first off, we need to isolate the exponent, or isolate the part of the problem with an exponent in it. So first thing we need to do here is to divide by 4 on each side. So we divide by 4. I get 3 to some mystery power is going to be 5. It's always a good thing to estimate what sort of a number we're looking at. I know that 3 to the first power is 3. The second power is 9. So definitely it's going to be 3 to the 1 point, I don't know, let's try 1.1-ish. Maybe 1.2-ish will get me about 5. Now, we're not going to solve these using guessing check, though. We need a method. And the method for getting this exponent out of the exponent is to take a log base 10 of each side. So that would mean log of 3 to the x equals log of 5. And what we know is that when we have a log of a number to a power, we can take that power and swing them out front. And so this is the same thing as x times log base 3 equals log base 5. And then we divide both sides by log base 3 because that's just a number. It's just a number I can't articulate. And I'm sensing that we're going to have an answer pretty soon. X must equal log of 5 over log of 3, whatever the calculator tells us that is. I'm going to pause and go grab a calculator. See, I grabbed a virtual calculator. So I needed to find log of 5, so I'm going to type in, do I have a log button on here? There it is, log of 5, close parentheses, divided by log of 3, close parentheses, and enter. And it tells me it is 1.46, so our estimate wasn't that bad. X equals 1.464. Woohoo! Let's move on to part B. Well, here we do have an exponent. It's 5, and so if we want to undo that power of 5, we would raise both sides to the 1/5. And so I get x equals 20 to the 1/5. And this is just a calculator problem. You could say x equals the 5th root of 20, whatever floats your boat. I'm going to punch it into my calculator. I'm going to say what is 20, and then to the, and then parentheses 1 divided by 5. Enter, and it tells me it's 1.82. Okay, x is about equals to 1.82. Last but not least, number C is written, actually last of this row, is written in log form, so I'm going to change it to exponential form. That would mean 2 to the x equals 5. I'm going to estimate that. I'm thinking about 2.2 or something like that, because definitely 2 to the second power is 4, and 2 to the third power is 8. So I'm going with 2.2. Same thing. We're going to take the log, same thing as part A. We're going to take the log of each side, so I get log of 2 to the x equals log of 5. And then we're going to take that little x and swing him out front and say x times log of 2 equals log of 5. And then we can divide both sides by log of 2. And whack-a-doodle, we get x equals something the calculator's about to tell me. Let's see how close my estimate was. Log of 5 divided by log of 2, and enter. 2.32. I seem to be lowballing my estimates. 2.321. Let's move on to the next page. Hey, calculator. Not the next page, the next row. Okay, so again, I've got a log statement. I'm going to rewrite it in exponential form. Base x to the 4th equals 16. You could either solve this in your head, knowing that 2 to the 4th power is 16, raise both sides to the 1/4 power, and then punch it into a calculator. But it's a lot healthier to recognize that the 2 to the 4th power is 16. Let's take a look at E. Again, rewriting it in exponential form. Base 7 to the 3rd equals x. That's just 7 to the 3rd, which is 49 times 7, which is, I'm going to guess, 243. Maybe I should check. What is 7 to the 3rd? Enter. Oh, I was wrong. 343. 343. And Algebra 2, you get to hear Dalen Thetford for a minute. Dalen says, ooh, that's sick. All right. Here we go. I think he stopped by because I was talking to myself and he was worried if I'd really lost it. Okay, number F. Again, it's in log form. I don't like log form. Let's try exponential form. Base of 5 right there. To the x equals 1/5. Best way to solve this is by knowing something. If you want to take a 5 and put it in the denominator, that exponent would need to be -1. So x equals -1. Do I know how to solve this without doing that? I guess you could take a log of each side. It seems really silly. But you could take a log of 5 to the x equals log of 1/5. Okay. Oh, I have a great idea. And I'm just going to, just if you're with me on this, man, we're going to rock this. Watch, this x can pop out. Log of 1. You could say this is log of 0.2 or 1/5. And then, you know, do the calculator action thing. Now, what I was thinking is if you were really this part as log of 1 minus, right? So we could problem. Oh, I'm having fun now. Let's see. Log of 1. This is 10 to what power is 1? 10 to the what is 1? That's 0. Hey, this is 0. 0. So x times of 5. Oh, it's so cool. Equals negative log of 5. Oh, this is amazing. I shouldn't be doing videos on my own because. And scroll down because then if you divide 5, you get 1. Oh my gosh, so much work. So much work. And it's all unnecessary if you just recognize right on up there that from here and then just, yeah, anyway. Lots of easier ways to do this. But. Okay, number 3, here we go. Show that each of the following is equivalent. You know, I'm giving you these because you're going to have problems like this on your test where it's going to be multiple. It's okay if you don't know how to show a lot of work. These are actually genuinely supposed to be multiple choice-ish problems. That said, log base 3 of 1/3. Well, let's see. Here we have a log. So if I were to multiply times 1 over 27, I would get 9/27 or 1/3, which is that. So that makes sense. And log is 2, so I guess that's what I'd write. Log base 3 of 9. And let's see. Oh, third, so that would be -3, and 2 minus 1 is -1. And let me pause this for a second. All right, and we are back. So let's see. Here in part D, this part is the same. And so you might ask yourself, how did they get out of that? Well, what they could have done is they could have said of 1 over 27 is the same thing as log base 3 of 27 to the -1, right? Because that's how we get 1 over 27. And that little -1 would pop out, and so we'd get negative log base 3 of 27. So it works out. Yay. It's not a lot of work to show. Actually, why did I make a frowny face there? Yay. Not a ton of work to show on these. Again, now. So here we go, doing our work to show. Number 8. Find the equation, blah, 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 blah. Things where you have an axis. I've always given you asymptote there and graph like that. I sure hope I'm recording and getting lots of beeping noises. Yeah, seem to still have power. We could, whoops, elsewhere, right there. Oh, come on, man. It could be shifted up. Or x-axis, so that's easy. So we just have this equation, y equals a times b to the x. So we've got an x and a y there, an x and a y there. Let's plug them in and go. 60 has to equal a times b to the 4th. And 15 has to equal a times b squared. And what I've always do is take one of them. I usually take smaller x. get squared times b to the fourth. And since 15b squared, 2 up top, if we divide both sides by 15, whack, b squared equals 4, and so b must equal 2. Now that we know that, I'll go back to, say, this equation, and let a be 15 over 2 squared, 4. So we get, for a final equation, I equals a times b to the x. Okay, 1 down, 1 to go. The next one's going to be a little bit gnarlier. Brace yourselves. And looking at all those decimals, I'm going to be pulling out the old calculator here. So we've got an x and a y and an x and a y, and they tell me an asymptote. So my basic equation now becomes this. Not y equals. I'm going to plug in this point. 18.25 equals a times b to the x plus 12. Right, because they gave me plus 12 right there. Okay. And then my other equation is, oh, fun, 793.25 equals a times b to the fifth, also plus 12. Now, don't freak out about the plus 12, because we can make it go away. We can make it go away by just subtracting 12 from each side. So I'm going to do that on each problem. Okay. And so here, 18 minus 12 is 6. So this is 6.25 equals a, b. And here, this is 781.25 equals a, b to the fifth. And now we're right back where we were last problem, just with some decimals and slightly higher exponents, but we're okay. So I'll take this problem here, this one here, because it's got smaller numbers. I'm going to solve for a, dividing by b squared. A is going to be 6.25 over b squared. I'm going to take this a and dump it into this equation, which becomes 781.25 equals, school's out, 6.25 over b squared times b to the fifth. Alrighty, and now we have a bunch of b's that cancel. And so I have 781.25. Come on in. We got lots of company on this video. 6.25 times b to the third. Okie dokie. So let's see. Now I'm going to have a calculator action here. First I'm going to do a little bit of work off to the side here. Divide by 6.25. And I'm not even going to try to do this in my head. B to the third equals, but I bet it's going to be something nice. Okay, so 781.25 divide by 6.25, enter. 125, ain't that amazing? Talking like Hulhauser. And so you could solve this by looking at it. B to the 5 to the third is 125. So B must be 5. And let's see, here's my equation for A. So A must equal 6.25 over B squared, 25. I'm thinking that's a quarter. I'll check it out. 6.25 divided by 25. Sure enough, it is. A is 1/4. A is 0.25 or 1/4. And so now we have an equation. Y equals A times B to the x plus that asymptote. Don't forget that we had the asymptote in there. Alrighty, let's take a look at the next page. Let's hide this dude. He's a persistent little dude, isn't he? Okay. Number 5. Number 5. You didn't have to, if you were stressing out about these things, don't. all it is just use the log properties to combine things. Like here, you're adding log statements, so that means you multiply the guts. So that's log base 7 of 16. Here, right, again, you're adding stuff, so you multiply the guts, so it's log base 7 of 2 times 5, 10 times 3, 30. Here, let's see. What I might do is I might swing that 3 back on up. So it's log base 5 of 2 to the third, 8. Sorry guys. Log base 5 of 2 to the third plus log base 5 of 4. Because now I have log of stuff plus log of stuff. So now I can multiply my stuff. It's log base 5 of 8 times 4, 32. Again, here, I'm going to swing this 4 on up, so I have a single log thingy there. So this is log base 8 of 3 to the 4th, whatever that is, minus log base 8 of 27. And when we're subtracting log statements, that means we divide the stuff. So I'm going to divide those things. So log base 8 of 3 to the 4th over 27. And 3 to the 4th is, well, 27 is 3 to the 3rd. So I'm thinking the final answer is log base 8 of, it's 3 to the 4th over 3 to the 3rd. So that's just 3. So I'm thinking this would be my final answer. Number C. Oh, and this is nice and easy because we don't have any numbers out front. So we just have a division, or we have a subtraction symbol. So that means we're going to divide the loggy stuff. So it's log base 8 of 32 over 4, which is log base 8 of 8, which I declare as 1 because 8 to the first power is 8. That's nice. And last but not least, let's see. I'm going to take that 3 and swing them on up there. So I get log base 12 of 2 to the 3rd. 2 to the 3rd is 8. So log base 12 of 8, and that's where I'm going to leave it. The end. Yeah, without using a calculator. That's all we're looking for. Now, here we go for number 6. Okay, these were just like some nasty problems on your quiz. Let's shrink it down a little bit. There we go. Number A is very much like a quiz question. I'm looking at this thing and thinking, wow, is there a way to rewrite that 4th root? And there is. What you could do, why am I writing so small? What you could do to write x to the 3rd and the 4th root of that is you could write that as x to the 3rd to the 1/4. And we're multiplying by x to the negative 5 over 4. Well, when you have a power raised to a power, you can multiply those powers. So that's x to the 3/4, and that is 3 times a 4th, times x to the negative 5/4. And just like I said on the quiz, if you have x to the 2nd times x to the 5th, you add the exponents. And so since, again, here, I have the same bases, I will add the exponents and get x to the negative 2/4, which is x to the negative 1/2. Now it says, don't use fractions and don't use negatives in your exponents. So I'm going to need to somehow make this not a negative up there. Well, I know that x to a negative power is 1 over x to a positive power. So I'm going to rewrite this thing as 1 over x to the 1/2. And I also know that x to the 1/2 power, a fractional power, can be written as a root. So this is 1 over square root of x. Okay, the next one is not so bad. Here I have x to the 2nd, and to rewrite that 5th root, I'm going to raise it to the 1/5 times x to the 8/5. And again, just like in the first problem, when I have a power raised to a power, I can multiply them. So this is x to the 2/5 times x to the 8/5. And again, just like right over here, when I'm multiplying the bases, I am adding the exponents. And if I add 2/5 and 8/5, I get 10/5, which is 2. Okay, let me bring this up and pause. Okie dokie. And now we have parts C and D. I'm just going to write it a little bigger just for kicks. Is B to the -2. A negative exponent means it can, whatever has a negative exponent can change floors in that fraction. Sorry if the volume's changing. I'm changing the position of this mic. So in a problem like this, x to the 7th isn't going anywhere. He's got a positive exponent. He stays put. B to the -3rd has a negative exponent, so he must go downstairs. B to the +3 downstairs. X to the -2 has a negative exponent, so he's going to change floors and go upstairs. X to the +2. And so is that B to the -2. He's going to fly upstairs. B squared. And now we can simplify things a lot. I have a bunch of x's up top. I have 9 of them, x to the 9th power. I have b squared up top and b cubed on the bottom, and so a bunch of b's will cancel. And I'm going to have x to the 9th on top and a b left over on the bottom. And I'm going to shrink that down with that one. And here we are on part D. On part D, again, well, what the heck, just for kick, there. I'm going to rewrite this thing a little bit bigger. It's 3, 5x to the -3, and a b over an x and a b squared. It looks like the only part of this that has a negative exponent is everything inside the parentheses here. So it's all going to go downstairs and have a positive exponent. So on the top, in the numerator, I still have that 3, this 3, and I still have the b. On the bottom, I now have 5x, but it's to the +3rd, times an x, times a b squared. Okie dokie, now it's cleanup time. So, okay, well I know that the top has a 3b, 3 times b. 5x to the 3rd means the 5 is cubed, 125, and the x is cubed, x cubed, times an x, times a b squared. And now I'm hoping that people see that some b's cancel. You have a b up top and 2 in the bottom, and some x's combined, because that's an x to the 1st. So final answer, we get 3 over 125, x to the 4th, and a b left over. Let's take a look at the last couple of problems here. Are we on? Yes, we are the last problem. You can always tell, I was thinking when I was making this thing, that you can always tell when I write a problem because of the language. I start using, words like a whopping 500 bulbs. So you know that I wrote this problem. And I made it up. It is not grounded in reality. It's just, I just thought it would be fun. So we've got daffodil bulbs. This part is true, man. You plant daffodil bulbs and you let them sit, and pretty soon you're going to have bulbs all over the place. And I have no idea how many years it takes for them to reproduce. But, okay. Let's see. So in 1957, there were 200 bulbs. That sounds to me an awful lot like an initial value. And 6 years later, they had 500 bulbs. I don't know how they counted them, but whatever. Those people at Daffodil Hills are pretty crazy. And so I'm curious whether you have any thoughts about whether this growth is linear or exponential. And I'm hoping that you realize that this growth is exponential. It's exponential growth. And there are a lot of ways of describing this. I'd probably say, because if you have 600, let's see, so to go from 200 to 500 bulbs, you multiplied by 2.5 in 6 years. And so 6 years after that, in 12 years, you'd have that amount. And again, you'd be multiplying by 2.5 because every new bulb sprouts old bulbs. So I'm going to say because every new bulb grows new bulbs. More new bulbs. Or you could say it's a multiplying pattern. Multiplying. Lots of ways to say this. So the biggest idea is if you just understand that this sort of growth where, sorry about this, where if you recognize that the growth doesn't depend on just a single rate, it depends on how much you have. So, you know, you have a certain amount and then it grows to a newer amount, and then this newer amount grows, each little part of this newer amount grows accordingly, and it grows even more. So anyway, I'm not a very good explainer of this stuff, but it is exponential growth, and talk to me in class and maybe we can make sense of it if I just did it in a crazily bad, annoying job. Let's take a look at part B. Phew! I'm going to maybe shrink down part. Alrighty, show that this is the equation. Well, people, it's by show, it doesn't mean use the equation and show it works. It means show that we can get that equation. So I know that if I have years and bulbs, at year 0, I have 200 bulbs. And at year, 6, there are 500 bulbs. Okay, so I now have 2 points on an exponential graph. So if I have this function y equals a times b to the x, I know that if y is 200 equals a times b to the 0, b to the 0 is 1, so my a value must be 200, right? Because b to the 0 is 1. And then if I use the second point to write an equation, 500. 500 equals a, which I'm putting in 200, times b to the x. This is very solvable. I can just divide both sides by 200, and I get b to the 6th power is 500 divided by 200, which is 2.5. I could whip out that ugly calculator of mine, and what we're going to have to do is raise both sides to the 1/6 power. And so I get b equals on 2.5 to the parentheses 1 divided by 6. Enter. 1.6164. So I get b equals 1.165-ish. And what was the equation we had here? Ah, there it is! Yay! So we have y equals a times b. Come on. 1.165 to the x. All right. Go away, little calculator. Part C. Part C, how many bulbs are there now? Well, 2017 is, and I did make this math easy, is exactly 60 years from 1957. So it has been 60 years. We have this equation. The number of bulbs is how many we started with times the growth rate, 1.165, to the number of years, 60. And so I'm just going to punch that into my calculator. 200 times 1.165 to the 200 tells me, boom, a big number. Did I? Oh, to the 200. Genius. Okay, okay, 200 times 1.165 to the 60. Enter. Good. Try to make numbers so that you wouldn't have that exponential notation. So I get y equals 1,908,031. Backing up the commas, and it looks like we are at 1.9 million bulbs. Wow, it's a lot of bulbs. Okay, and now, last but not least, let's minimize that. I should have made this problem, I should have made it 3 million for part D instead of 2 million. I think I made it 2, huh? Yep. Mrs. Hill claims that she's going to solve bulb or sell bulbs on eBay once she has enough. And that enough has to be at least 2 million. So I'm going to again take my equation and I want to solve for a number of years. So my equation is y equals number of bulbs. We are number bulbs equals starting value times growth rate to the number of years. So I'm going to plug 2 million over here. 2 million equals 200 times 1.165 to the x. And solve this thing. First thing to do is to divide by 200. Okay, be gone, little 200. Whack. And so I get 1.165 to the x equals, go away 0, go away 0. This is 20,000 divided by 2, so 10,000. And if we're solving for an x, we would take a log of each side. Log of 10,000 equals log of 1.165 to the x. And we did that so that we knew that we could pop out this little x right there. So this is x times log of 1.165 equals log of 10,000. Now, if you're a really clever cookie, you don't need to do this part on a calculator because this is log base 10. 10 to what is 10,000? 10 to the 2 is 200. 10 to the third, 10 to the fourth is 10,000. So this whole side is just 4 equals x times log of 1.165. Doesn't always work out that way. Sometimes these numbers you just have to punch into a calculator, but in any event, we can now divide by this thing. Divide by log of 1.1, I don't know what I was doing there, 65. Divide by log 1.165. Whip out the old calculator. Clear. 4 divided by log of 1.165, parentheses, enter. 60.308. X equals 60.30. What did I give you? Tell you how precise you had to be? To the nearest 0.01 years. So 0.3. I'm going to round up because we had 0.8, so 31 years. Which makes sense because we're almost from part C. We were almost at 2 million. And it's growing exponentially, so it shouldn't take much more time. Apparently, it's going to take 3/10 of a year. All right, Algebra 2, I hope that somebody watches this and finds it useful. See you later, people.